Science doesn't stall at the microscope anymore. It stalls at the decision point. What to test next, and how fast that choice can compound. So what happens when that decision loop leaves the notebook and starts running at machine speed? Science automated measurement years ago. The real bottleneck is deciding what experiment to run next, and one robot just ran 688 in 8 days. Think about a chemist searching for a better battery material, catalyst, or drug process. Each knob matters: composition, temperature, pressure, mixing time, additives. Turn 5 knobs with 10 options each, and you already have 100,000 possibilities. Humans can measure samples quickly, but choosing the next most useful trial under that kind of uncertainty is slower. That is the contradiction. Science can generate data fast, yet still guesses its way forward. And the critical shift is not a faster robot arm. It is a lab that learns after every single run. A self-driving lab closes the loop. First, researchers define an objective function, maybe higher hydrogen yield, better ionic conductivity, or a more stable formulation. Then software maps the experimental space and estimates where useful results might be hiding. Instead of brute force screening, active learning or Bayesian optimization models choose the next experiment for maximum information or best expected performance. Robotic instruments execute it. Sensors like spectroscopy, chromatography, or electrochemical tests capture the outcome. The model updates, uncertainty shrinks, and the queue changes in real time. That is different from plain automation. Adenary has framed its SD Labs platform around reducing the number of experiments needed to hit target properties, not just increasing throughput. And the concept is no longer theoretical. In 2020, Liverpool's mobile robotic chemist worked 21.5 hours a day for 8 days, autonomously running 688 experiments in a photocatalyst search, reportedly about 1,000 times faster than a human on that task. In 2023, Berkeley Lab's A-Lab autonomously synthesized 41 novel inorganic materials from 58 candidate targets in 17 days. So what happens when the decision loop runs at machine speed? Science stops spending most of its time on low-information trials. It can search battery chemistries with millions of combinations, catalyst recipes, or synthesis conditions by prioritizing the next informative step instead of scanning everything blindly. Over the next 10 to 20 years, the strongest labs may look less like isolated benches and more like networked search engines for matter, linking models, robots, sensors, and remote instruments to compress years of iteration